Hello, everyone. This is chapter 11, part 2. Chapter 11, part 2 will focus on angular momentum. We will develop a conservation of angular momentum law and talk about problems associated with the conservation of angular momentum. And then we're going to talk about gyroscopes, which are neat little objects which utilize angular momentum to do some pretty cool things. They're found in phones, planes, pretty much any type of machine that needs to know its orientation. We'll talk about those later. It's a lot of fun. But first of all, before we can even define what angular momentum is, I want to go back and look at linear momentum and how we defined it, how we derived it, what it was, and how we derived the conservation law of linear momentum. So Newton's second law, if you recall, says that the sum of all the external forces acting on a system of masses is equal to the total mass of that system times the acceleration of the center of mass. Putting this in derivative form, we have the velocity of the center of mass, the time rate of change of the velocity of the center of mass, times the mass. And if you recall, we moved the mass inside because it's constant, move the mass inside the derivative. And so we defined something called the linear momentum, P. I'm going to try to remember to draw my vectors for you, at least for some of this. But we defined a linear momentum, P, as m times v, where v is the center of mass velocity, the linear velocity. We stated that there is a linear momentum in x, in y, in z. Each has its own linear momentum. And furthermore, we said that if the sum of the external forces is 0, then the time rate of change of the momentum, which is equal to P final minus P initial, is equal to 0. And this gives us a conservation law, which states that if there are no external forces on a system, the initial and final momentum, linear momentum of that system is conserved. The initial and final momentums are equal for the entire system. We use this most notably in collision problems, in a few other problems. Remember that basically this was the impulse J, which was equal to the change in P. If that is 0, if there's no impulse, there's no force acting on the system, then the final linear momentum of the system is equal to the initial linear momentum. Things can change as long as the total final momentum is equal to the total initial momentum. And that gave us the conservation law. You can go back to chapter 9, look through that, remember that, although I think you all have that down at this point. So let's take a look at angular momentum and try and define a quantity of angular momentum and see how it compares with Newton's second law. Angular momentum is one of the fundamental quantities of the universe. We often describe things like electrons by their angular momentum. It has its set of laws that govern it, conservation law for it, much like mass, linear momentum, and energy all have conservation laws. So we need to start with a mathematical definition of what the angular momentum is. And remember that angular momentum is momentum an object has due to rotation, not due to translation. So let's imagine that we have a hydrogen atom. And there's a nucleus, and there's some little electron that is rotating around at constant radius, r. And this electron has some angular velocity, omega. And it also has a tangential or translational velocity, v, along the curve at every point. But it's rotating counterclockwise, which is a positive angular velocity. And so we say that this has a quantity called angular momentum, which we give the letter L to. And L is going to be equal to the mass of this particle times R cross V. And R is the radial vector of, so this is our R. And obviously our V is our translational V. So recalling from our cross product that A cross B is equal to A, B sine of the angle between A and B. Another thing to remember is that if we have some constant times A cross B, we can always pull the constant into the cross product. So this could be CA cross B, or it could be A cross CB. We can always pull a constant into the cross product by multiplying it by either of the terms. We're going to need that in a minute when we derive this. But for now, let's look at this R vector and this V vector. If we cross them, we see that we are rotating R to V, which is a positive rotation. Another thing that we could say is that the angle between R and V is 90 degrees, which is positive. So this becomes, I'm going to write this as RMV sine of the angle between R and V. Let me write it that way. Since this is sine of 90 degrees, L is simply, it's usually more often written as this, MRV, where R and V are perpendicular to each other. So sometimes they'll write it as the perpendicular component of R times V. Another thing I want to note is that because R is constant, we know that V is equal to R omega. If I plug that in here, I get that L is MR perpendicular squared times omega. Now, you should also recall that for a point particle, the moment of inertia is mr squared. Therefore, we have that L, the angular momentum, is equal to the moment of inertia of a particle times its angular velocity. It looks a lot like P, the linear velocity, or the linear momentum, which was mv, where instead of m, we have a moment of inertia, and instead of a tangential velocity, we have a rotational velocity. However, I caution you that the units are slightly different. Let's look at the units of angular momentum. Well, first, let's look at the units of linear momentum. This is just kilogram meter per second. What are the units of angular momentum? We get kilograms meters squared times radians per second. So we basically have an extra unit of distance in the angular momentum. Neither of these have a name. They are the angular momentum and the linear momentum. But for now, that's our working definition. This right here is our working definition of what the angular momentum of a single particle is. It's L is equal to mass times R cross V. A more functional definition for later is that L is I omega, and we'll get to that. However, let's actually derive what the angular momentum is, and we're going to see a cool relationship which will tell us a little bit more, give us a better mathematical description of what the angular momentum is and how we can use it. So, recall that I just said that this was m of r cross v, and if I move the mass inside, I get that this is r cross mv. If I take the time rate of change of this, okay, so I want to take the time rate of change of the angular momentum. In order to do this, I have to use the chain rule. So I get that dl dt is dr dt crossed with mb plus r crossed with d dt mb. Okay. Now, a couple things to note, that dr dt is v. Secondly, that dmb dt is simply the force, a force. So we get the dl dt is equal to v cross v plus r cross f. And note that for a cross product, two vectors or a vector cannot cross itself. If the vectors are parallel or anti-parallel, you get a cross product of 0. This is r cross f, and r cross f, we already know what that is. That is a torque. Okay. Further, if this is a net force and this is a net torque, so dl dt is r cross f, which is another way of saying that the net torque acting on the system is equal to the time rate of change of dt. Furthermore, because L is I omega, as we saw earlier, this we can write as I times d omega dt, which is I alpha. So the two things to take away here are that we have the L dt is equal to m times r cross v. This is equal to m r v dt, which is equal to the net torque. So net torque is the L dt, which is I alpha. So L is equal to I omega, which is also equal to m v r, which is also equal to m r squared omega. And the torque is equal to I alpha. Okay. So let's come back to the relationship between all of these. And if the torque is I alpha, that means that the net torque is equal to the time rate of change of the angular momentum. If this is 0, we get that since dl dt is equal to L final minus L initial, and if that is 0, then we get L final is equal to L initial for a point particle. The other thing that in this course we will almost always consider that the rolling without slipping conditions apply. So therefore A translational is equal to R alpha, and V translational is equal to R omega. So L can be equal to M R squared omega or M V R, and torques can be equal to I alpha or I A translational over R. Okay, good enough. That's it. Those are the equations that you need to remember, and we'll discuss those in depth in a moment. So Last thing that I do need to bring up, however, is imagine that this particle, this electron again, is going around with some angular velocity around the nucleus where the axis of rotation goes through. Coming out of the page is z hat, positive z hat. So the actual omega vector is along z hat, and the L vector is also along positive z hat, because L is the moment of inertia times the angular velocity vector. However, if we were on the other side, we would see that this electron is rotating with negative angular velocity, and therefore this vector coming out of the page is the negative z hat. Well, actually, I shouldn't say that. If the positive z hat comes out of the page, then omega is along the negative z hat direction, and L is along the negative z hat direction. What I'm getting at, what I'm trying to get at here, is that these vectors, the angular momentum vector, is a pseudo vector, much like when we discussed the angular velocity vector. The angular momentum vector points in the same direction as the angular velocity vector, not the same direction as the angular acceleration, the same direction as the instantaneous angular velocity vector. And that depends on where your frame of reference is. So it's a pseudovector, which means that it doesn't follow all the mathematical laws or rules pertaining to vectors, the usual vector rules. That's something you'll get into in a math class later on. For us, we just need it to determine which direction is rotating. So all you need to remember is that it points in the same direction as omega. So L is in same direction as omega. The angular momentum points in the same direction as the angular velocity, always. All right. So we talked about a single particle, but what happens if, say, we have a whole bunch of particles and they're all rotating around some common axis of rotation? Let's say it's z hat coming out of the page. Okay. What we have is big L is the total angular momentum of the system, and it's equal to the sum of each individual particle from n1 to n, or from 1 to n. So we would have the sum of 1, of 2, and of 3. This, keep in mind, is mvr. So it's each individual particle's radial vector and velocity, or radial vector squared times omega. All you have to do is sum them up for the total system. We'll do a problem like that in a little bit to show how that's done, but for a system of particles, we get L. Now, if we have some solid object that isn't just a collection of particles, let's say a wheel, and the wheel is rotating with omega, we know that L is therefore equal to the sum of the mr squareds times omega, right? But every mass in this wheel turns with the same omega. So omega is just omega. This quantity here is actually the moment of inertia of the system. If you go back and recall that the moment of inertia was the sum of the moment of inertia for every particle. So what we get is I times omega for the object. For a wheel, I is mr squared over 2, and therefore L of this wheel would be mr squared over 2 times omega. Okay? The total mass times the radius squared over 2 times omega. Simple enough. We'll always deal with solid objects that are that we know the moment of inertia, so they'll have high symmetry, or we'll deal with systems of particles that only have a few particles. You'll see that most maybe 4, maybe 5, I don't know, on the homework. But it's not too hard. We can add them all together and get the total, and then treat it as if the system as a whole has an angular momentum L. All right. So, translation versus rotation. I wanted to talk really fast about something that comes up often. While Newton's laws for linear motion look a lot like the mathematical equations for rotation, there are some huge differences you need to know. So let's talk about linear motion. And linear motion versus rotational motion. And first of all, we know that in linear motion, we talk about a displacement. I'm writing x here, but x could be y, could be z, any linear motion. In rotational motion, when we talk about a displacement, we talk about a change in angle. In linear motion, we talk about a velocity, which is the displacement divided by time, or the time derivative of the displacement. In rotational motion, we talk about omega. This is displacement. This is angular velocity. Okay. And finally, obviously, we talk about an acceleration, and we talk about an angular acceleration. Here, the law is the sum of the forces, or the external force, is equal to m times a of the center of mass. Here, the law is that the torque is equal to I alpha. That looks a lot alike, but there's a huge, huge difference that I cannot stress enough. The units here, the units of force are newtons. They are kilograms, meters per second squared. The units here are kilograms, meters over seconds squared, times meters, times rads. Remember, rads aren't actual units. They're kind of a placeholder. So this looks a lot like a Newton meter. But torques are not Newton meters. So torque, not a Newton meter, which is a joule. Torque times the change in angle times the displacement is joules, okay? So a torque by itself is not energy. A torque times a rotation is energy. Much like force times the change of time is an impulse, which results in a change in momentum. Torque times the change in angle results in a change of rotation. Okay. Yeah, that's do I want to say that? This is yeah, that's fine. Force times distance times change of x is work. This is actually work. So this is the same as work. Torque times a displacement is actually the same as work. Force times time is the change in momentum, which is mv final minus mv initial, which was the impulse, J. Torque times the change in angle is the change in omega, and that is work. It's a change in energy. force times distance is work, change in energy. So while it's somewhat okay to say that the torque is equal to the moment of inertia times the angular acceleration, that is the angular equivalent to F equals ma, it's not exactly true. Mostly because there's that pesky extra unit hanging on. Again, as I said, angular momentum and torque, the units are what they are. Torque has units of kilogram meters squared over second squared. Angular momentum has units of kilogram meters squared over seconds squared. Torque is not energy until you multiply it by a change in angle. That's all I really wanted to say about those. It's something that's easy to forget. You just have to remember that you don't do any work until the torque is applied over some angular displacement, okay? All right, let's do a couple of quick examples. Example one, I'm gonna describe this really fast and then we're gonna solve it. So let's go back to that electron, and let's say this electron is rotating at a distance of r equal to half a meter with some angular, I'm going to call these initial, angular velocity of 2 rads per second, okay? And then it moves. It gets bumped. It ends up being moved out to a further radius where the radius final is 1 meter. And so we want to determine what is the final angular velocity. And we note that I'm going to pretend this mass is 1 kilogram. Okay. So if there is no net torque acting on it, it just slides out on its own to a position that's further away for some reason, then we know that L initial is equal to L final. Furthermore, L initial is m r times b, okay, which here is m r initial times b initial, but since b is r omega, this is m r initial omega initial, r initial squared, sorry. So what is L initial? We get 1 kilogram for the mass, 0.5 squared, and 2. So 1/2 times 2 is 1 times 1/2. This is 1/2, and remember, kilogram meters squared over seconds times rads, okay? Or here it's kilogram meters squared over seconds. Now, what is L final? Well, L final is m r final v final, or m r final. I guess I should make these big R's. R final squared, omega final squared. And now what we can do, using this, we can solve for omega final, and we'll do that on the next slide. So just remember that the initial L was 1/2. So remember that L initial was 1/2 kilogram meters squared over seconds. All right, so we wanted, if R final was 1 meter and R initial was 0.5 meters and omega initial was 2 rads per second and the mass was 1 kilogram, we want to know what is omega final. So we can use that L initial is equal to L final. And from this we see that m R initial v initial, which is m R initial squared omega initial, is equal to m R final squared omega final. Let's just concentrate on this part of this equation. Cancel the masses, and we get that omega final is simply R initial squared omega final over r final squared. And this would be 1/2 squared times 2 over 1 squared. So this is 1/2 rad per second. Okay, what is L final? Well, you should already know because the angular momentum is conserved, L final had better be 1/2. We can check that though with R final. V final is equal to M R final squared omega final, which is 1 times 1 squared times 1/2, which is 1/2 kilogram meter squared per second. But we knew that because it had to be equal to our L initial here. We can also find V final, although knowing that V final is equal to R final omega final, we can find that this is 1 times 1/2, which is 1/2 meter per second. Let's go back and check one thing. So the initial velocity here would have been, V initial would have been R initial omega initial, and R initial was 0.5, and this was 2, so this was 1 meter per second. So if we go back and look, V initial and V final, V initial was 1 meter per second, and V final is 1/2 meter per second. L initial was simply L final. They were both 1/2 kilogram meter per second squared, and omega initial versus omega final was 2 rad per second and 1/2 rad per second. So so when it moved out, the angular momentum didn't change when it changed position. When R initial went from 1/2 meter to R final being 1 meter, the angular momentum didn't change. It stayed 1/2 kilogram meter squared per second. However, the initial angular velocity went from 2 rads per second to a final angular velocity of 1/2 rads per second. And the velocity went from 1/2, went from 1 to 1/2. Okay, 1 meter per second to 1/2. Okay, so we see that as the object moves outward, this should be, yeah. As the object moves outward, it actually slows down by conservation of angular momentum. That's because as R gets further away for the angular momentum, so for M V initial, R initial to equal M V final, R final, if R final is getting bigger, V final has to go down. And because V is equal to R omega, if R is increasing, well, I should say that since this is also omega, so we can see here that as R increases, V and omega both have to decrease. In fact, omega has to decrease more than V because R is squared. So just keep that in mind. In order for angular momentum to be conserved, what happens is the further out from the axis of rotation an object travels, the slower it actually rotates. That's in contrast to our solid rotation. but that's fine. Okay, just keep that in mind. Simple. So example 2, in this, I'm going to imagine I have a massless rod, okay, and I'm going to say that this is 0.5 meters, this side, and this side is 1.5 meters. So at 0.5 meters, at 1 meter, and at 1.5 meters from the axis of rotation, I have a mass here, I have a mass here, I have a mass here, and I have a mass here. So call this mass 1, mass 2, mass 3, and mass 4. And this whole rod is going to rotate with positive angular velocity in a counterclockwise direction. And what I want to know is, I want to know what L of the rod is. And if omega is 4 rad per second, I want to know what L is, assuming that omega is 4 rads per second. Okay. And then I want to know what V1, V2, V3, and V4 are. Okay. So I want to know L, and I want to know V1, V2, V3, and V4, assuming that omega is 4 rads per second. So remember that L is simply the sum of each of the particles from 1 to n. So let's find L1, L2, L3, L4. Okay, so for mass number 1, L is M1, R1, V1, which is M1, R1 squared omega. M2 is M2, R2 squared omega. M3, R3 squared omega. And M4, R4 squared omega. And then for each one, we can use V is equal to R omega. So we could find either one of those first. I'll do the V last. But let's find L. So L is M1 R1 squared omega plus M2 R2 squared omega plus M3 R3 squared omega plus M4 R4 squared omega. And I should have said that M is 2 kilograms for each mass. They're all the same. Okay, so knowing that, I'm going to take this out, and I'm going to take M omega times R1 squared plus R2 squared plus R3 squared plus R4 squared. And that gives me 2 times 4 times 0.5 squared plus 0.5 squared. Note that even though this is minus in the opposite direction, it's still 0.5. It's the distance from the axis. Then plus 1 squared plus 1.5 squared. And so this answer is 8 times 1/2. So 1/4, 2/4. So that's 1 1/2, 3 halves. So I get 3.75 times 8, I get 30. So this L is 30 kilogram meters squared per second. Okay. And V1, for instance, I'll let you do all the rest of these, but V1 would be R1 times omega, which is 0.5 times 4, which is 2 meters per second. By contrast, V4 would be R4 omega, which is 1.5 times 4, which is 6 meters per second. So in this example, most of the angular momentum is actually contributed by mass 4. the angular momentum of mass 4 by itself was 2 times 1.5 squared times 4, which is 8 times 1.5 squared, which is 18. 18 kilogram meter squared per second. 18 of the angular momentum out of the 30 is being provided simply by M4. Even though they're all the same mass, it's actually most of it is being provided by that. The angular momentum of mass 3 would be 2 times 1 times 4. So that would be 8. So only M2 and M1 are only providing 2 kilogram meter squared per second of the angular momentum each. Okay, so just keep that in mind. An object rotating further out at the same speed has greater angular momentum than if it was rotating inside. That's pretty obvious, so I think. So I already solved this. I don't need this slide. I don't know where. Okay. So let's talk about that whole conservation of angular momentum thing again, though. So if there is no torque acting on the system, no net torque, we say that L initial, L final minus L initial is 0. And that means that L final is equal to L initial. That doesn't mean that the moment of inertia of certain objects can't change. In fact, we're going to see a couple of problems where the moment of inertia definitely does change. And in fact, in that first quick sample, we saw that the moment of inertia, when it went from R was equal to 1/2 to R was equal to 1 meter, right? The moment of inertia of the object initially was mr initial squared, and the moment of inertia final was mr final squared. So this would say that I initial omega initial is I final omega final, and we see that I initial is mr initial squared, omega initial is mr final squared, omega final. And therefore, what you're seeing is that as the radius, if the radius changes, then omega has to change. And if omega changes, then the radius has to change, as long as the conservation of angular momentum is true. We're going to use that fact over and over again to solve problems, that the moment of inertia can change and the angular velocity can change. So if one changes, the other has to change. It's a balancing act. And we'll see that right now with this first problem. So this first problem, I hope all of you have watched figure skaters. But a common occurrence in figure skating is the figure skater will be spinning with their arms out and then pull their arms in and kind of tuck their body down, and it will dramatically increase their rotational speed. This happens because since they're on ice, we can assume that there's no friction between their skates and the ground, and therefore there's no torque acting on the system at all. What's happening is they're changing their moment of inertia, which is causing their angular velocity to change as well. So in this problem, this first problem I want to do, I'm going to have a figure skater who has, their body has a moment of inertia of 66 kilograms per meter or times meter squared with her arms outstretched. I'll draw a picture in a minute. Each of her fists has a mass of 3 kilograms, and when her arms are outstretched, each of those fists is 1.1 meters from the central axis of her body. But when she pulls her fists into her chest, each is only 5 centimeters away, and the moment of inertia of her body decreases to 52 kilograms per meter or times meter squared. If she initially was spinning with an angular velocity of 25 rads per second when her fists were outstretched, what is her angular velocity going to be once she pulls her fist in? And we can assume that her fists are points and there are no external torques acting on her body. All right, so let me draw a picture of this really fast. So we have this figure skater, and she has her arms outstretched, and she is spinning around with positive omega. If we go back and look, this is 25 rad per second. Her fists have a mass of 3 kilograms. Her body has a moment of inertia of 66 kilograms meters squared, and her fists are at a radius of 1.1 meters. All right, and then when she tucks herself in, so her fists are tucked in, she's going to get omega final, and that's what we want to know. She's going to spin faster. So using conservation of momentum, we can use that because we know there is no net torque on her body. We therefore know that her initial moment of inertia is equal to her final moment of inertia. But what is her initial, or I'm sorry, her initial angular momentum is equal to her final angular momentum. But what is her initial angular momentum? So for her body, it is I of her body, omega. And I should state that here, this was 52 kilograms meters squared. So I of her body times omega, initial, plus I of her fist times omega initial, and there are 2 of those. So she has 2 of these. Okay. What is I of her fist? Well, if we treat them as point particles, it's the mass times the radius squared. And each fist is 3 kilograms, and the radius is 1.1. So this gives us 3.63 kilogram meters squared. So her initial angular momentum is 66 times 25 plus 3.63, and don't forget there's 2 of these, times 25. Okay. So her initial moment of inertia is 2 times 3.63 times 25 plus 66 times 25, which is 1,831.5 kilogram meters squared per second. Now, what is her L final? Her L final is I final omega of her body, omega final, plus 2 times I final of her fists times omega final. And I final of her fists are now going to be MR final squared, which is 3 times 0.05 squared, which is 3 times 0.05 times 0.05, which is 0.075. 0075. So this becomes, if I pull the omega final out, I get I of her body final plus 2 times the I of her fists, which is omega final times 52 plus 2 times 0.075, which is 0.015, so 52.015. So let's move to the next slide. And we get that L initial is equal to L final. And L initial we said was 1831.5, and L final we said was 52.015 times omega final. So omega final is, symbolically, I can write this as I total times omega initial is equal to I total final, I total initial, omega final. So omega final is I initial, omega initial over I final. So this is 1831.5 over 52.015. So that is 1831.5 divided by 52.015, which is 35.21 rad per second. And remember, initially, she had an angular velocity of 25 rad per second. So she increased her angular velocity by 10 radians per second by pulling her arms in. That's pretty fast. It's a pretty steep increase. One thing that you can double check is remember that I omega initial was 1831.5 kilograms meters squared per second times rads. And this is I final is 52 times 25, which is, wow, sorry, 52 times 35.21 basically, which is still 1830, right? So 1831.5. I'm writing this to illustrate that the angular momentum of the figure skater doesn't change. What changed was she changed her moment of inertia. She actually reduced her moment of inertia because this was the initial times the initial, so final times the final. So if you change the initial moment of inertia, you increase, if you decrease the moment of inertia, you increase the angular velocity, is what I'm trying to say. Pretty straightforward. There's a couple of these in your book. One shows a person sitting in a chair with weights in their hands, and they spin around and then they pull the weights in and the chair spins faster. You can prove it to yourself pretty easily by doing that experiment at home. Put something heavy in each hand and spin around and then pull it in and see if you increase your speed. It works in reverse as well. If you ever watch figure skaters, they'll spin, and then as they come out of the spin, they'll throw their arms wide. That increases their moment of inertia, which in turn reduces their angular velocity. It's something that you intuitively know by being human in how you move. The next problem is a little bit more fun. It's technically an inelastic collision with angular momentum. So basically imagine that there's two wheels on an axle shaft. I'll draw this as well. That passes through their centers of mass. The first wheel has a mass of 55 kilograms and a radius of 0.75 meters, and it's initially spinning with an angular velocity of 65 rads per second. The second wheel is at rest and it's not touching the first wheel. It has a mass of 33 kilograms and a radius of 0.25 meters. Suddenly the two wheels are brought together in an inelastic collision. The two wheels stick together to form a single composite wheel that turns as a solid object. If we assume angular momentum is conserved and is not lost during the collision, which can be true, we could, a couple of common problems is like dropping a mass on top of another mass. Unfortunately, I don't think we get to do that in lab, but it's one of the experiments we should have done. So if we assume that angular momentum isn't lost during the collision, what is the final angular velocity of the two wheels? Okay, so what we're talking about here is we have a wheel that is spinning about its axis, okay, and we have a second wheel, a smaller wheel, that's also spinning, or that's at rest, and it's shoved in so that both the wheels together are in effect welded together. So what's going to happen here is this is going to have some initial angular momentum and some initial moment of inertia, and then the final moment of inertia will be the moment of inertia of both discs, and there's going to be some final angular momentum. Okay, so first of all, remember that I is mr squared for both. Secondly, initially, the angular momentum of the system, L initial, will be I of, let's call this big plate, plate A, small plate, plate B. This would be IA omega A plus IB omega B, but it's at rest. And L final will be IA plus IB. Remember that when we have a composite system, its moment of inertia is the moment of inertia of the individual parts of the system times omega final. And we want to know what omega final here is. Assuming there's no net torque, we have conservation of angular momentum. So what we have here is we have IA omega A is equal to IA plus IB omega final, or that omega final is IA omega A times or divided by IA plus IB. Now IA is, we said this was 55 kilograms and 0.75 meters in radius squared. This is 15.47 kilogram meters squared, and IB is 33 and a quarter 0.25 squared over 2. So 33 times 5. This is 1.03 kilogram meters squared. So our answer here is 15.47 divided by, that would be 16.5 times, it was initially spinning at 65 rads per second, times 65 rads per second. So what we get is 15.47 divided by 16 times 65. I get 62.84. 62.84 rad per second. So there was a decrease in angular velocity of 2.16 rads as they came together. This problem is also done. You can find this problem all over the internet. Look up angular inelastic collision. This is actually kind of how your bicycle or your car transmission will kick down a gear. The clutch plates basically bring the mass away bring the other gears away. And it's kind of a cool, quick problem. It's something you might see on a quiz. It's something you might see as the first part of a problem on an exam. It almost is identical to the inelastic collision problems that we had, except with MV replaced by I omega. It's not too hard to understand. The only physics involved is conservation of angular momentum and the moment of inertia times omega. So these problems aren't too bad. You usually just have to find the moment of inertia of the objects, know how to add them together or take them apart, and figure out what the change is, assuming there's no torques. If there are torques, then you can use the constant angular acceleration equations, which we did last time in the last lecture. And other than that, it's not too bad. I actually think this stuff is easier than what I did in chapter 11 problems part 1. So the final topic that I want to talk about is the gyroscope. And this is a lot of fun. I recommend you look up gyroscopes on like YouTube, but before you do, let me try and describe them. So a gyroscope consists of some kind of mount that rests on the ground and a rod, and then attached to that rod is usually a wheel that can rotate. And this wheel can rotate in around, okay? But initially, let's look at what happens if, oh, and I should say that at this pivot point, there's no friction, okay? So if the wheel's not spinning, what happens is the force of gravity just causes this wheel to fall over, right? Just falls over and hits the ground. However, what happens if the wheel's spinning? And we assume there's no friction between these points, okay? So first of all, we need to look at this wheel, okay, with the shaft coming out of it. Okay, and this is where the point is. But this wheel can go around, and if we assume that we're looking at it this way, then omega is positive. And if this wheel's spinning, so if you're looking at it, it has omega coming out of the page, right? It also must have some angular momentum, L, equal to I omega, and the L vector is also coming out of the page, right? And if that happens, let's look at, from this point to here, you have a radius vector. And from here down, you have a force of gravity, mg. So acting on the gyroscope, you have R, you have F equals mg, and you have this angular momentum vector that's coming out along in the same direction as R, okay? If it wasn't spinning, the angular momentum vector wouldn't be there and the wheel would fall over. But when it's spinning, what happens? So R cross F is the torque. If we look at it from above, kind of, we see that F goes down and R goes this way. So R and F, right? This is a torque that R rotated that way means that the torque is going to point this way. So let's look at this from overhead. This is the rotation of the whole pivot arm. This is the wheel, and there's a torque going this way, and there's an L vector, an angular momentum vector going that way. Now remember that we said that the torque was equal to a change in the change in angular momentum with time. So what happens is this torque, due to gravity, causes the whole apparatus to rotate around, or what we call to precess, okay? The whole thing rotates. Now, first of all, assuming that L is constant, we have some delta V, and sorry, let me take that back for a minute. We have some d phi and some dl, okay? And what we want to define is something called omega, big omega, which is phi divided by t. So first of all, okay, we know that dl is equal to the torque times dt, and we know that the torque is caused by R cross mg. Since R and mg are perpendicular, this is just mgr, right? Okay, so we get that phi here, d phi, L d phi is equal to dl. This is R d theta is equal to S, right? So d phi is dl over L, and so dl over L divided by dt, but this is the same as dl dt 1 over L, The LDT here we know is the torque. So P is mgr over L. But remember that L is simply I omega. And because if we assume that I is mr squared omega, canceling stuff out, we get that the precession rate, which is the change in angle as it goes around, is G over R omega. And there's a few profound things to talk about here. First of all, that the precession rate doesn't depend on the mass of the wheel, but it does depend on omega. If you spin the wheel faster, it precesses slower. It goes around much slower the faster omega gets. Secondly, note that this seems to be defying gravity, right? As long as there's no friction at the point of contact, as long as there's no friction where this rod, what happens is the force of gravity turns into a torque that causes the whole apparatus to spin around and around and around. Third thing, essentially you have G is R omega times the rate of precession. That means that if you are on some alien planet, you could find out what G was if you knew what omega and little omega and big omega was and R was. But lastly, and this is by far the biggest part of this, is that for the gyroscope, which spins around, okay, since the precession only depends on G over R omega, if there's no net torque on this, angular momentum conserved and it just spins around forever. Not only that, but it always spins around aligned with G. The precession, omega, okay, is always aligned to positive Z, and G is down. What that means is if you could put this thing in a cage, in some kind of cage that was free of any friction, where it could spin around on its own, set this thing spinning, you would always know and set sensors around. So imagine you have a gyroscope that's in a cage and the thing can spin. You set a sensor here and here and here and here, and you put little sensors on the edges of the gyroscope, then it knows which way the gyroscope is oriented. This is how, like an automatic pilot in a jet would know which direction is down, because the gyroscope always points so that it spins around so that it's spinning with Z hat along its rotational axis. That means that you can have a mechanical way of telling which direction down is. So you could put an autopilot on and have it make sure that the gyroscopes all align and the plane flies level. You could have it so that your phone knows when you turn it sideways, because the gyroscopes are no longer aligned with straight down, and therefore, well, the gyroscopes are, but the phone is not aligned to the gyroscopes anymore, and therefore it knows to flip the picture on your phone. You can have satellites that use them to maintain stable orbits. Gyroscopes are really, 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 really neat. Unfortunately for us, they are pure plug and chug questions. They're worth checking out. They seem to defy gravity, as I said, but they do prove a couple things. They prove that the angular momentum vector is a real thing. It's not a fake vector. There is an angular momentum quantity to the gyroscope, which is conserved. But you guys know that. For those of you that were in lab the day that I rotated the wheel and had you shift it 90 degrees, and you could feel the wheel fights being rotated, angular momentum is an actual quantity. It's not something we make up, like when we say that potential energy of 5 joules. When something's spinning, it resists having its angular momentum changed, and you have to apply a torque to change that angular momentum. So we know that angular momentum is a physical quantity. If you go on to study quantum mechanics, angular momentum of subatomic particles is one of the defining characteristics. Their angular momentum is one of their defining characteristics. The gyroscope proves that angular momentum is a real thing, and it's one of the most useful tools that we have that you probably don't even realize. A lot of the things, the tools that you use or vehicles you fly in, use them to figure out where they are. Anyway, so that's it for chapter 11. It's a kind of fun chapter. Sorry, I was a little tired throughout this lecture. But next time, I'm going to give you some, probably 6 or 7 problems that I'll go through that won't be the homework problems, but there'll be other problems. And I'll go step by step through them and solve them, just to make sure that you understand how to do these problems. I don't want to leave you with these 3 or 4 little examples. I want to give you real examples. And then next week, chapter 12 is actually a really easy chapter. We're going to do it in one lecture, one of these lectures. It's all about equilibrium. The condition for equilibrium is that the forces acting on the system and the torques acting on the system are 0. So if you get done with this and you want to read ahead, read chapter 12. It's pretty easy, pretty light, pretty fast. The other side of chapter 12 is something called elasticity, which is stress and strain, and that's really easy plug and chug stuff. And then we're going to be moving on to reviewing the concepts we've learned since exam 1, so chapters 7 through 12. So anyway, I hope you're all happy and healthy. Stay safe, and I'll talk to you soon. Bye.